Hey guys, I hope all is going well. We're going to do some hypothesis testing for slopes today. I chose this screen because I didn't want you to be able to tell that I didn't comb my hair. Did it work? Let's go to the notes. Hypothesis testing for slopes. I covered this a little bit in a previous video, but we'll go over it a little bit more detail today. This shouldn't be too long of a video. I'm going to just show you kind of the underlying theory on these notes, and then I'll show you some examples in Excel that should be helpful for your homework and your projects. But let's just remind ourselves real quick that we're starting off with a population equation. Actually, no, let's start with a research question, because that's what we do in the past, and that's probably the easiest thing to start with. So let's ask, how does economic growth affect inflation? So economic growth, you guys know what that is. That occurs when we make more stuff, sell more stuff, everybody's got a job, so that's the economy growing, or we could be in a recession, which would be a negative economic growth. Inflation is when price levels go up. So usually we have like a theoretical reason for asking questions like this, so you can think about why this might be. Well, if everybody has a job and everybody's making a ton of money, that means people are buying a lot of stuff, which might increase prices. So we might expect economic growth to increase inflation. On the other hand, if we were including some developed or less developed countries in our analysis, we might observe a very high inflation rates in countries with low economic growth if, for example, the government is printing a lot of money to build up an army or something like that. That can lead to inflation, but that really is going to probably be in a situation where we have high inflation but low economic growth. So Venezuela might be an example of something like that right now. So we have reasons to believe that this could go in two directions, but I just want to point out, you want to kind of think about the theoretical reasons you might have a relationship between your X and Y, or independent and dependent variables. After we ask our research question, we could write out a population regression equation. And so I'm going to write it in terms of what I'm actually looking at. So inflation, that's my Y, my dependent variable, equals beta naught, some population intercept, plus beta 1, the population slope, times, we'll just call this GDP for gross domestic product growth. That's how we're going to measure economic growth. When, as you know, we do not believe that this relationship will hold perfectly in the population data. So we had an error term right here. So remember, we always have 4 components, and then we really have 5 once we have this error term. For any simple linear equation, we have a dependent variable, an independent variable, a slope, and an intercept. These two guys are our unknown population parameters. This is the stuff we're trying to estimate. And so our research question, though, is about the slope, right? So if beta 1, the population slope, is 0, then the answer to this research question is no, right? Because if beta 1 was 0, 0 times GDP growth is 0, and inflation does not have GDP growth in its equation. So that would be a no answer to this research question. The answer to that research question would be yes, if beta 1 is anything other than 0. So that's going to help us with the topic of the video, which is hypothesis testing. So we have a null hypothesis and an alternative hypothesis. Beta 1, that's our unknown population slope. So we will be writing our hypotheses in terms of that unknown population parameter that we're trying to ask our question about? Well, if the answer is no, then the null hypothesis will be true. Beta 1 equals 0. Beta 1 does not equal 0 for the alternative, then that answer would be yes to this research question if the alternative is true. So that should be familiar to you. Notice that's a two-sided test. When we use the analysis tool pack in Excel, it's always assuming that we're doing a two-sided test. So that's worth thinking about. I think most of the book problems assume you're doing a two-sided test too. And oftentimes we treat all questions about slopes as two-sided tests. So now the next step in our statistical analysis will be to go and actually estimate. So estimated sample regression equation. And so just like before, we went from mu to x bar, we're going from betas to b's. So our estimated sample equation line will be inflation equals b naught plus b1 times GDP growth plus our sample errors, also known as residuals. So this same components, y, x, except now this is a sample slope because it's our estimate, it's our sample estimate, and this is our sample intercept. Now again, notice we don't really know what the population intercept is, but our research question is about the slope. So really for the most part, when we're doing regression, as I've mentioned before, we really care more about our slope than our intercept. Although you can do hypothesis testing for the intercept if that's an interesting thing to do. So let's talk about, we want to know so that these sample slopes are a random variable, because if I took a different random sample, I would get a different slope, right? Every time I took a different random sample, I did get a different slope. However, those random slopes will be centered, guess where? At the truth. So here is our parameter, our population slope is right there in the middle. Our B1s, our sample slopes, will be from a bell curve around beta 1. It's going to be a T distribution, actually, as you know from X bars and mu. So it's exactly the same thing. The only difference is now we're talking about a slope. And then what we're going to do, so we're going to actually observe. So we'll put equals 0 question mark because we'll center this at the null hypothesis. And then we'll be able to set up a rejection region. This is two-tailed, right? So we'll have lines on both sides. And so these areas, that's our rejection region. And the area of that is going to equal sigma, right? Alpha, the significance level. And then I'm going to go ahead and I'm going to eventually, when I get my data, I could land over here. So say we get this particular slope of 5. I don't know what it's going to be, but say we got 5 and that landed there, then we'd reject the null hypothesis. We would know we landed there if we looked at the p-value, which would be the areas out here, right? -5. So we could compare our p-value to our significance level, or we could compare our t-statistic to a critical value. And you guys know that stuff from before, from chapters 9 and 10. So everything about that is the same. Really, the only thing new here is that we're doing this with slopes instead of doing it with either sample means and population means or differences in sample means and differences in population means, which was chapter 10. Now we're doing the same process, but we're doing it to our slopes from estimated regression equations. So I will see you guys in Excel for a second, so we'll see how this actually works out, how we get our estimates. and decide whether a slope estimate is statistically significant. Now, when people say statistically significant real quickly, what they mean is that they've chosen the alternative hypothesis. When somebody says they have a statistically significant slope estimate, they've rejected the null and accepted the alternative. So that's what the meaning of statistical significance is. Okay, so I'm going to use that terminology a lot. I encourage you to use that in your project. And just generally, when people say statistically significant, they mean that the null hypothesis is rejected. All right, so I will see you guys in Excel real quick. Okay, here we are in Excel with some data on inflation rate and the GDP growth rate. So here I have Australia's GDP or economic growth rate and Australia's inflation rate. I was going to take this as an opportunity to show you guys some different types of data that I mentioned before but didn't show you an example of every type. So on this first page I have time series data because the variation in my data set comes from different time periods. So in 1985, this growth rate, this is how much Australia's economy grew. So it grew 3.82% in 1985. And in that year, it had an inflation rate of 6.74%. So these two numbers, this X and this Y, are paired together by this year. And then I have a different year, so I get a different growth rate, different inflation rate, and so on. And so this is a time series data set from 1985 to 2016. So that's one way we might measure the relationship between inflation and growth rate. Now look at this data for a different way to think about it. So here, this is called a cross-sectional data set. And so now notice that I have a bunch of different countries. And for each country, I have an economic growth rate and an inflation rate. So these two, this X, negative 1.82% growth in Afghanistan in 2015, is paired with this inflation rate right here, negative 1.53% inflation in Afghanistan in 2015. Similarly, in Angola, we have a growth rate and inflation rate. So this is a different type of data set because although I have the same variables, growth and inflation, economic growth and inflation, the reason that those vary in this data set is because they occurred in different locations. So that's called a cross-sectional data set. Now finally, here's panel data, which combines both data types. So this looks just like what I had on the first tab, right? So this basically is the time series data set, except now I've added a new label for country. And then down here, I start again with a new country. So the variation in this growth rate and inflation data comes from both variation across time and variation across space. So that's kind of like the ideal data set because you get the most variation. And variation in our two variables is good because we want to see how those things are changing together or separately to estimate whether one affects the other one or not. So variation in our underlying data is good. And so you're going to have one of those three types of data sets: time series, cross-sectional, or panel data. Now, when you download your data, it's unlikely that it's going to be perfectly formatted for you to do regression. So notice that I wanted to show you when you download your data, there's a good chance that it's going to look differently. So this is what this data, I downloaded this data from the World Bank, and this is what it looked like when I downloaded it. So this is the GDP data, and I kind of had to organize that into columns myself after the fact. The vast majority of time spent among statisticians, data scientists, analysts is actually organizing data because it takes a lot of work to collect and organize data. Once you have collected and you're organized your data for your project, it's kind of like downhill from there because you just have to run the analysis at that point. So that's why I again encourage you to work on getting your data sooner than later. So now let's go ahead and actually estimate our regression equation. So we know from the notes at the beginning of this video what's going on. We're proposing that there's this population relationship, but now we're going to test it. So I'm going to do data analysis regression. I'm going to highlight first input y range. What's our y variable? That's inflation. So I'll click on the label, Control Shift down or Command Shift down to get that whole column. Looks like I have 32 observations. Now I can do that with the growth rate because that's our x variable. I included labels, so I need to make sure that box is checked. You can use some of this other stuff down here like residuals for your homework. Some of that is valuable. But for now, we'll just keep this as it is, and E2 looks like a good place for it, so I'll hit OK. And now to do my hypothesis test. So the number one thing I want you to always get used to doing, let's always interpret the slope here. So this is going to be our slope estimate. That is our B1, our sample slope estimate. And to interpret this, we'd say, on average, when Australia's GDP growth rate increases by 1 unit, 1%, inflation rate increases by 0.25. So that's our estimate in our bell curve, a slope of 0.25. Now the question is, did that land far enough away from 0 for us to reject the null hypothesis? And the answer is going to be no on this one because our p-value is 0.429. And so if we remember the common sigma, so the most common one is 0.05, 5% significance level. So that's the most common. And that's kind of the standard that people use. Our p-value is much larger than that. But the other two common ones are 0.01. Clearly, we're larger than that. And 0.1. So 5%, 1%, and 10%. Our p-value is much larger than any of those kind of common levels of significance. So in this case, we would fail to reject the null hypothesis because our p-value is greater than all of those. We can also see that our t-stat of 0.8, although this does not provide us with a critical value, that is going to be lower. Just from your experience, you know that t-statistics to reject, probably you need one of at least 1.5 or 2. So we're not really even close to that range. But I would encourage you to just use the p-value approach for these slope problems because those can just be immediately compared to these common significance levels. For your project, I encourage you to kind of be holistic and use all of them. Because you could imagine getting a p-value that lands between some of these, in which case you would reject the null hypothesis at certain levels, but not others. But in this case, we will not reject our null hypothesis that the population slope is 0 at any of these conventional levels. So that's our time series estimate. Positive relationship, but not statistically significant. So let's try that with cross-sectional now. I encourage you to pause the video and try to do this as practice before I do it. So what we'll do is data analysis, regression. It's going to preload what I did last time, but now I have some different sizes of data sets here. So Y is inflation rate. Much more data, 231 observations. X is GDP growth rate. Labels is clicked. E2 still looks good. So let's go ahead and click OK. So now here's my slope. Here's my p-value. Now I have a negative relationship, so let's interpret the slope. Across countries in this data set, on average in my data, when GDP growth increases by 1%, inflation tends to decrease by 0.3%. Okay? Is that statistically significant? Yes. We would reject the null hypothesis in this case. So this p-value, 0.0008, is less than 0.01, 1%. It's also less than 0.05 and 0.1. So here we would say we reject the null hypothesis at all conventional levels of significance, all conventional significance levels, because our p-value is less than 1%. Therefore, it also must be less than 5% and also less than 10%. So that's kind of interesting. We use the same variables, economic growth and inflation. Here we got a positive estimate that was not statistically significant. But then when we looked across countries, we got a negative estimate that was very statistically significant. So that's totally worth thinking about and very interesting. And we're kind of discovering new things about the world through data right now, right? So when I looked across countries, it was more likely that I included countries where we have high inflation and low growth. So let's see, I was going to look for inflation, but here's a country. Zambia had negative growth, but 10% inflation. So a large inflation rate, 10%, but actually negative growth rate. Here's another big example right here. Ukraine has negative 10% growth basically, and like 50% inflation. The difference is here we were only looking within Australia, and Australia is more of kind of like a developed country, so it's probably going to have a more like our first explanation where we have more people buying stuff when there's big growth. That leads to inflation. Versus cross-sectionally, we probably have a lot of scenarios where we have bad institutions that are leading to low growth and high inflation. Here's Angola is kind of another example right there. Negative growth, but 10% a high inflation rate. So that can show you how what type of data you get really can matter. And it's really cool sometimes to be able to do those comparisons if you'd like to go above and beyond. Doing comparisons with different types of data sets in your final project would definitely boost your final project score if you're interested in anything like that. So now let's do our panel data here. So again, I encourage you to go ahead and try to pause the video and practice this, but then I'll go ahead and do it too for you. Data analysis, regression. We have our inflation rate here. Economic growth rate here. So now we have about 89 observations in this panel data set. Let's put this in F2. Okay. So now we got back our positive relationship. So now in this cross-sectional data set, on average, when GDP growth rate increases by 1%, inflation rate increases by 0.19%. So that's more similar to our first time series estimate, which makes sense. We have Australia, United States, and Germany, so pretty stable, developed economies there. Here is our p-value. This one we're going to fail to reject again, right? But we're really close. Because one level of significance that would be possible if we were using sigma 0.1, we would fail because our p-value is larger than 0.1, but it's very close. So if I got that type of a result in a project, I'd probably want to point out that it was very close. Sometimes we use terms like marginally statistically significant, which kind of means like, well, it wasn't statistically significant using this 10% significance level, but it was really close. Okay? So that is how we implement hypothesis testing for slopes in regression using Excel. And you're going to do this again in chapter 15 with multiple regression, which basically means you're going to have more independent variables listed here. And the idea will be the same. Every single one of those will have its own p-value, and you can just individually do the slope interpretations, the p-value interpretations for each slope in your data set. We also have the same interpretation of significance F. Significance F is another type of p-value. Notice in these simple linear regressions, that significance F number is exactly the same as our p-value. That will stop being true when you have a multiple linear regression, again, meaning that you have multiple dependent variables. So that's going to change the significance. That one's kind of the p-value for your entire regression model instead of just one specific independent variable. The reason that they're the same so far is because our entire regression model in this case is just one independent variable. All right, so let me know if you have any questions about this. I will upload this spreadsheet and the notes with the video, but I will talk to you guys soon.